Okay, are you seeing it?
Okay, you're good.
Good morning. I'm Randy Zimmerman. I'm one of the chief engineers at Titus. I've been at Titus 39 years, and I've spent a lot of that time around terminal units, testing and developing and doing applications. So let's see, I can't advance the slide.
Are you on Zoom or are you clicking on the PowerPoint?
I I don't know. Um, I'm gonna stop the share.
That's fine.
Going to go back. Okay.
Yep.
You want me to start over or?
No, you're good to go. Go ahead.
Okay. So anyway, we're gonna cover a number of things today to kind of give you a good some good information on terminal units. We're going to look at types and applications. We'll be covering single duct boxes, exhaust boxes, series fan powered, parallel fan powered. We're also going to look at selection and sizing. So we'll be looking at how do we size inlet ducts, how we select fans, a little bit about electric coils and hot water coils, and then we'll finish up with kind of some ideal installation. So first we'll look at types and applications. Now the simplest terminal unit is the single duct VAV. And most manufacturers make these units in a very similar fashion. We actually pioneered this design back in the 1970s. It's got a round inlet, and that round inlet's fitted with an inlet sensor that's going to measure velocity. And that velocity sensor then is going to be piped to a VAV controller inside the enclosure on the side of the box, which also has a built-in actuator generally to move the damper to regulate the airflow to the room. And this unit configuration is not accidental. We've got the round inlet, we've got the rectangular discharge, and we know that the round inlet is the most efficient way to deliver air to the room because, like I always tell people, air is round. You can put it in a rectangular duct and it just goes oval. So anyway, we want to have a round inlet. Then we try to size that rectangular discharge for at least twice the cross sectional area of the inlet. And that's so that as air expands, going over the damper and expands to fill the rectangular casing and discharge ductwork, we'll get some static pressure regain. And that'll lower our pressure requirement to get air to the room. Also, that rectangular discharge is, the most convenient connection for locally fabricated duct runouts, and we can easily tap into the sides of those rectangular ducts for our diffuser takeoffs. Now, of course, the most common application for a single duct box um, it is usually for handling interior spaces. Um, if they don't have a coil on them, they get cold air, 55-degree air from the air handler, and they can be used to offset internal heat loads in the space. Now, in order to do that, we generally have to have a pressure independent controller on the box where we can set a minimum and a maximum airflow. So we've got our design cooling airflow, and then the damper closes down to a minimum ventilation airflow that meets the requirements of ASHRAE standard 62.1. And because the controls are pressure independent, they automatically compensate for changes in inlet static pressure. So if there's a sudden rise or fall in inlet static pressure, the controller, since it's monitoring the velocity, then readjusts the damper open or closed to keep it at the desired air volume. Now we can take that same box and we can set the minimum and maximum airflows to the same value. And now suddenly we've got a constant volume box. And constant volume boxes are generally used to provide ventilation or used in critical environment applications where we have to get a certain number of air changes per hour to meet the requirements of ASHRAE standard 170 or to meet the ventilation requirements of ASHRAE 62.1. Now, of course, if we're going to be using this box just to get air changes, but we can't change the air temperature, we're going to have some other way of maintaining the temperature in the room. And that could either be adding a reheat coil to this box or having some kind of separate supplemental heat in the room. Now, if we want a box with reheat, we're still going to usually receive our cooling from the air handler. And this box might be used to handle perimeter spaces. But whenever we go to reheat, we need to have a minimum of at least 3 different flow rates. We still have our design cooling flow rate. We still have our minimum ventilation flow rate, but then we usually want to have at least one more flow rate, and that would be the heating airflow. Now, in some cases, people will select a single heating airflow and just do constant volume during heating. But with today's digital controllers, it's not difficult. It's usually an option to do VAV heating as well. So this would be a box that would handle a perimeter zone. Now, here's a sequence that a lot of people don't understand, and that's single duct VAV with auto changeover. Some people call that a heating cooling auto changeover, and some people mistakenly think that boxes with reheat coils are auto changeover because they can go from heating to cooling. Well, that's kind of a misnomer. When you're doing single duct VAV with auto changeover, it's usually a project that involves like leased space at an office park where you've got a suite that somebody's renting, and there's a lobby, and there's restrooms, and a few offices, and a break room, and maybe a stock room or something. And if you want to put VAV boxes in there, generally those spaces are being served with a rooftop unit. And that rooftop unit's going to provide cooling, but it's probably also going to provide gas-fired heat. And so if you're going to get heating and cooling from your rooftop unit, the boxes need to be able to detect the temperature of the air being supplied so that they can correctly operate to know whether they should be opening or closing to get back to set point. So basically, that usually involves having an inlet-mounted temperature sensor of some sort to clue in the controller when the supply air changes. And the controller then needs to know whether the supply air is hotter or cooler than the temperature that you're trying to control in the space. So that's how we would handle small lease spaces with a rooftop unit. Now, exhaust terminals, I've got 2 different ones depicted here. One of them is round, the other one is rectangular. Just kind of depends what your duct configuration looks like, which one you should be using. Anyway, exhaust terminals are used in applications where we not only have to control the airflow into a room, but we also have to control the airflow out of the room. And that usually is involved in critical environment applications like healthcare, operating rooms, patient rooms, clean rooms, any place where we're trying to do room pressurization. We can either create a positive pressure in the room or we can create a negative pressure in the room. Putting the room under positive pressure creates a protective environment where, we might be a good place to put a patient that's got a compromised immune system, where we're trying to keep things from reaching the room that could harm the patient. Negative pressure um, creates infectious isolation. So if we had lab animals or something that had some kind of highly infectious disease or something, we would want to put them under negative pressure, because that would prevent contamination of the adjoining spaces. And the most common way to achieve that room pressurization is to put an offset, either a positive or a negative offset, in the airflow settings between the supply box and the exhaust box. In some cases, people would tie those controllers together and have them communicating back and forth. Now, here's what you don't want to do. You don't ever want to use a single duct supply box as an exhaust box. Now, people have done it a lot. People do it every day and people get away with it. But the problem here is um, that contractors get confused. Um, if you hand them a supply box, they know exactly how to install supply boxes because they do it every day. When you hand them a supply box and tell them that it's an exhaust box, the first thing most contractors will do is go, let's see, for exhaust, I need to flip the box around backwards so that the inlet is pointing away from the room. Well, the inlet on the box is still the inlet. So usually what happens after that is I'll get a call and say they're trying to balance these boxes, but we're not getting a good signal on the airflow sensor. And of course, the explanation there would be, well, you've got the sensor pointing in the wrong direction and it's right behind the damper now. So the damper is shadowing the sensor. So the way to correct that situation, since it's usually way too late to redo all the duct work, and they may have 50 of them installed like this, the most common fix is to remove the sensor, flip it around the right way, and move it further downstream so that you can get a good airflow signal. Now, it's still not an ideal situation because the aerodynamics of the airflow going backwards through the box, the way it was not intended to flow, creates a lot of turbulence and a lot of pressure drop and probably some noise too. So even if that correction's made, you're still going to have some issues. So the best thing to do is just don't use supply boxes as exhaust boxes. Now let's move on to fan powered terminals. We make many different models for different purposes. We've got underfloor boxes, we've got low profile boxes, we've got lots of different types of fan powered terminals. But all fan powered terminal units can be divided into two categories. They are either series fan powered or they're parallel fan powered. Now, the series fan powered box, if you look at this cutaway, you'll see that it's kind of defined by the location of the motor and blower assembly. You'll see that they're on the discharge of the unit. So on the inlet panel, we've got a round inlet that's going to get our cold air from our air handler, and it's fitted with a velocity sensor and a damper. Then we've got our wide open induction port, and that's open generally to the ceiling plenum. Now, all of the airflow mixes and goes through the blower to get to the room. That's why it's a series box, because the primary and the plenum air streams are going to mix and both go through the blower in series. This type of unit is most commonly found in tall buildings. Like if you go to places like Chicago, New York, Boston, they've been using series fan powered as the standard for nearly 40 years. Um, They provide relatively constant air motion in the room, give you constant sound levels. Um, you're getting pulling free heat from the ceiling return. And then you can also have additional electric or hydronic heat mounted at the discharge. Now, I get asked this question a lot. Is it possible to duct the plenum intake back to the room? Yes, it's absolutely possible. In fact, in healthcare applications, it's actually a code requirement. What you have to be careful of is not creating too much pressure drop on that induction port. So you want it to be as unobstructed as possible. Um, these units also operate at very low inlet pressures. Rather than running your fan system at 1 to 1.5 inches of inlet pressure, I see some people running as low as half an inch on series fan jobs. So that's a big advantage. They're saving a lot of energy at the building fans. And of course, one of the things people like about fan powered terminals are that they can do night setback operation, maintaining night temperature set points without turning the air handler back on nights and weekends. So they kind of handle the setback on a room by room basis without the need of kicking on the main system. So both series and parallel fan boxes have advantages and disadvantages. The advantage of the series box would be you're getting improved room air motion and getting a lot more air changes in the room. So it should feel fresher. You're getting that constant sound level. You've got the reduced inlet pressure. And since the fan is driving the noise level of the box, most manufacturers offer quiet versions of their series fan powered boxes to bring down the overall sound level. Now, as far as disadvantages, well, the fan's going to be running continuously if you want to move air to the room because you can't push that primary air through a blower that's not running. So whenever the building's occupied, the fans need to be running in these units. And then also the fan and blower have to be big enough to handle the cooling design airflow to the room. Uh, you'll see that parallel boxes could have much smaller fans. Now, the parallel fan powered box, if we look at the layout here, you see the fan's not at the discharge. The fan is usually tucked back inside the unit, and it's got a backdraft damper on it. And that's usually just a gravity operated flap damper that is there to prevent the primary air from being lost out through the blower because this unit, the fan only runs during heating. So it's a parallel fan box because the primary airflow goes around the blower to get to the room. So the air mixing between the plenum air and the primary air occurs after the blower because the cold air never sees the blower. So we've got to have that backdraft damper to keep that air from being lost to the ceiling. Now these units, just like the series, are pulling free heat from the ceiling plenum, but we can put additional heat on the units. We can put electric heat at the discharge, or we can put hot water heat at the discharge. But the standard location for a hot water coil on a parallel box is usually on the induction port. Now, if you're using parallel fan boxes, you're going to have to go back to the higher inlet pressures, like 1 or 1.5 inches. But the unit can still do night setback control without turning on the air handler. Now, these boxes tend to be found in smaller, low-rise buildings and predominantly in warmer climates. You know, like I said before, series boxes get used in tall buildings up north. Now, as you come down towards the south, you start seeing more parallel fan boxes. When you get to Dallas, if you're putting up a tall building in Dallas, it's about a 50-50 split on whether or not it's going to be series or parallel. It all depends on the preference of the design engineer. Then when you go further south from Dallas and you go to somewhere like Houston, you'll find that they use series boxes down there just because that's what they're used to using. So it's kind of a combination of building size and building location kind of determines whether or not you're in a parallel or a series fan market. Now, if we look at the advantages and disadvantages of the parallel box, the advantages would be the fan only has to be big enough to handle the heating design airflow. So it may only be half the size of the fan that you would find in a series box. The fan only runs during heating. So that means the box is very quiet during cooling. Now, the disadvantages of the parallel box would be you're getting modulating sound levels. You're getting one sound level at maximum cooling, a different sound level at minimum cooling, and then the sound jumps up when the fan turns on. And anything that draws people's attention to by modulating like that would be considered an annoyance for the occupant. You've got those higher inlet pressure requirements. You've got varying airflow on the diffusers, which means you have to be more careful selecting your diffusers so you don't get into any situations where you've got low velocities on the diffusers and you've got air dumping from the ceiling. That's just dropping in a straight column from the ceiling, causing discomfort for people sitting below. Now, one of the other things that people often forget to consider on parallel boxes is air leakage. That series fan box has a cabinet that changes from a neutral pressure to a slightly negative pressure as the primary damper modulates. The parallel fan box is under a large portion of the cabinet is under positive pressure in the cooling mode. And since you've got access doors to get into the motor and blower, and you've got wiring pass-throughs and other items, and you've got that backdraft damper, there's many sources of leakage on the fan cabinet. And that really hurts the efficiency of the parallel fan box. Now, there's been a question in the industry for a long time about which fan box is more energy efficient from a whole building standpoint. And ASHRAE commissioned a research project called RP 1292 a number of years ago. They got 3 manufacturers to send large and small series and parallel fan units to Texas A&M University. They tested the units for every aspect of energy. Then they built a computer model of a building that could be moved into different climate zones like San Francisco, Chicago, Boston, Houston, and run at different time of day schedules, and then looked at the whole building energy usage. And if you ever pull this report off the ASHRAE website and make it to the 400th page, it says which one was more efficient. It says it depends. You know, if you're careful sizing and selecting these boxes, you could get an equal result from series or parallel. Now, to me, that was the perfect answer because all manufacturers that make these boxes make both kinds and they don't care which one you buy. They cost about the same. But this would also not outlaw one box or the other because I know some engineers and some engineering firms are just more comfortable using one than the other. So this didn't outlaw the use of any of these boxes. But the problem with that report was that all the test samples only had the older PSC fan motors because that was the predominant motor when the project was conceived. But by the time the project wrapped up, ECM had gained a major foothold, and a lot of people wanted to know how the results would have been different with ECM. So a group of interested parties got together, pooled their money, went around ASHRAE in order to get this done quickly, and had the new samples from the same manufacturers sent to the same researchers, and they reran the model for the ECM units, and it basically showed that the series fan powered unit with ECM um, was a clear winner because the series box allows you to take more advantage of the much higher efficiency of the ECM. That's the programmable motor. And one of the results of all this research has been that energy codes are now often requiring that if you've got a product where the fan not only runs for heating but also runs for cooling, so that would be like a fan powered terminal, a room fan coil. Energy codes now require the motor have a minimum operating efficiency of 70%. And that's not achievable with the older PSC motors. They generally have an efficiency range of 20 to 60%. The ECM, depending on who you talk to, has a minimum operating efficiency of 70 to 80%. But oddly enough, when you turn down the speed on the ECM, you can easily get efficiencies in the high 90s. So you can have a tremendous energy savings using ECM over the older PSC motor technology. So let's look at sizing and selecting. My golden rule for sizing inlet ducts, I never want to oversize my inlets. That can cause a lot of trouble as far as controllability. You can actually get into situations where the damper being mostly closed all the time actually makes more noise than if you would have gone with a smaller damper. And my golden rule is to try to size my inlets for a maximum inlet velocity as close to 2,000 feet per minute as possible without going over by much. So I use a 6-inch inlet right up to 400 CFM. I use a 8-inch inlet right up to 700 CFM. I use a 10-inch inlet up to 1100 CFM. And that gives me excellent controllability. I'm not going to be creating excess of damper noise. And it also gives me a very comfortable 85% turn down with no loss of control accuracy. Now, if I'm doing a constant volume inlet on a box, I've got a much more flexibility because I don't have to consider the turn down effect. So I can size those for anywhere from 1,000 to 2,000. So I can oversize a little bit for constant volume if I'm trying to lower my sound level or my pressure drop. Now let's look at fans. You'll see that we've got a couple different fan curves here. One is a PSC fan curve and one is an ECM. You see that they look totally different. The PSC curve has the maximum curve, then like the 1-row coil curve, then the 2-row coil curve, then it's got a minimum curve down there. And that minimum curve is what we call the 600 RPM curve. The PSC motors widely used in this industry are usually sleeve bearing motors that don't properly lubricate if you operate them at less than 600 RPM. So you got to stay away from that bottom curve. You never want to be near it because you could easily overheat your bearings and burn up your motor. Instead of a motor lasting 10 or 12 years, it may only last a few months. Now, the ECM curve, you'll see, is flat along the top. And that's because the ECM is a smart motor. It's programmed. It's actually, we program them to compensate for changes in external pressure. So if you set an ECM for 1,000 CFM and you go downstream and you start closing down balancing dampers, you'll see the motor automatically speed up to give you the same 1,000 CFM. So that's why it's got kind of a funny looking fan curve. So my golden rule for selecting PSCs is to select PSC fan motors in the top 25% of their range. That allows the motor to run cooler and more efficiently. like I said before, you never want to be down around that minimum uh, curve because uh, PSC motors, when you turn the speed control way down, they tend to hum. They tend to develop a very annoying hum, the low frequency hum that goes right through ceiling tiles is very annoying. So sometimes people shoot themselves in the foot by oversizing the blower and thinking they'll turn it down real low and it'll be really quiet, and they get the exact opposite result. Also, we don't want to burn up our fan motors by dropping below that minimum curve. Now, ECMs are a totally different picture. They've got ball bearings, so they technically don't have a minimum airflow. Now, we program our motors with a minimum airflow because we know that they can start to pulsate and run rough if you try to run them too slow. So we try to set in a minimum operating speed into all of our motors before we ship them out to keep people out of that situation. Now, I like to select ECMs in the lower 50% of their range, if at all possible. They run fine at the top end of their range, but you're going to get higher efficiency and quieter operation in the bottom 50%. So if you can afford to have slightly bigger units in the building, I think you'll get better performance and better energy efficiency. Now, here's what you don't want to do. I see a lot of people just as a default assume that they're going to have a quarter inch of discharge static pressure at the job site. So they select the boxes for a quarter inch of downstream pressure. But then when the boxes actually get to the job, they find out they've got actually less than a tenth of an inch. And that can actually move the selected operating point from one side of the minimum curve to the other side of the minimum curve. And that's when fan motors start to have very short service life because they don't lubricate properly and they can overheat. And that's on PSC fans. Now, as far as electric coils, there's a few things to look out for. First off, we get a lot of questions about low kilowatts. Somebody will say, why can't I order a 480 volt three phase heater for 1 kilowatt? Well, the problem there is that the element wires, the higher the voltages and the lower the kilowatts are for an element, the smaller the diameter of the element wire has to be. So the wires get very, very small and very, very they get very small and they can get very brittle as they heat up and cool down. So you're going to get a lot of premature failures if you make element wires too small. That's why we have established minimum kilowatts available for all the different voltages and phases that we offer. It's also important to know that terminal units are generally limited to a total current draw of 48 amps. So if you're trying to put too large of a heater onto a unit, it may not be available. Also, you have to figure on fan powered units, the fan motor current also has to be included in that maximum total current draw of 48 amps. Then the other thing to consider is discharge temperatures. You have to limit the temperature of air being delivered from overhead diffusers. Now, UL says that the maximum allowable discharge temperature from a duct mounted electric coil is 120 degrees, but you wouldn't want to do that. The hotter the air is coming in from ceiling diffusers, the more buoyant the air is, and the more the air will stick to the ceiling rather than mixing with the room air and getting the ventilation air down to where the occupants in the room are. So ASHRAE has a guideline that recommends that maximum leaving air temperatures from overhead diffusers should not be more than 15 degrees Fahrenheit above the desired room temperature. So try to limit try to limit that leaving air temperature on our diffusers. I'd never try to select it more than 90 degrees. Now, when we're selecting a coil, there's some guidelines for different types of boxes. For instance, let's say we've got a single duct box with an electric coil, and it's got its entering air at 55 degrees, and it's got a heating airflow of 350 CFM, and it's got a heating capacity that we've determined is of 2.5. We know the leaving air temperature equals the entering air temperature plus the kilowatts times 3160 divided by the CFM. And plugging in those numbers would give us a leaving air temperature of 77.6. Now, the guidelines for this type of unit would be if we assume 55-degree entering air, we have to have at least 70 CFM per kilowatt to prevent elements from overheating and getting dropouts on high temperature limits that could cause our discharge temperatures to vary. So by having at least 70 CFM per kilowatt, that's going to limit our discharge temperature to 100. But if we want to go with the ASHRAE recommendation of not being more than 15 degrees above the room temperature, then you want to have at least 90 CFM. And that will limit our leaving air temperature to 90 degrees. That's easy to remember. 90 CFM per kilowatt gets you to 90 degrees. Now, here's an example of a fan box. Let's say it's got entering air temperature of 55, plenum temperature of 70, heating capacity of 7 kilowatts, a fan airflow of 1,000, and a minimum primary airflow of 200. Then the mixed air entering the coil is going to be equal to the entering air times the primary minimum airflow plus the plenum times the fan airflow minus the primary minimum divided by the fan. And if we plug in all the numbers, it gives us an entering air temperature on our coil of 67 degrees. Now, if we want to know our leaving air temperature, that would be our coil entering air temperature plus the kilowatts times 3160 divided by the fan, which gives us a leaving air temperature of 89.1 Fahrenheit. So if we've got a fan box with a 20% primary minimum and an entering air temperature of 55, we need to have at least 95 CFM per kilowatt to prevent overheating. And it would be even better to have 135 CFM per kilowatt because that would limit our air temperature to 90 degrees. Then for a parallel example, if we've got entering air 55, plenum air 70, heating capacity 5.5, fan at 600 CFM, primary maximum at 1,000 CFM, and primary minimum at 200 CFM, we can calculate our coil entering air temperature at entering air times the primary minimum airflow plus the plenum times the fan airflow divided by the fan plus the primary minimum, which equals 66.3 degrees. Now, if we want to know our leaving air temperature, that's going to be our coil plus the kilowatts times 3160 divided by the fan plus the primary minimum, and that equals 88 degrees. So for a 20-degree primary minimum with a 60% fan, that's 60% of the primary design maximum, and an entering air temperature of 55, we need to have at least 92 CFM per kilowatt to prevent overheating, but it would be better to have 135 CFM per kilowatt to limit our air temperature to 90 degrees. Now, as far as hot water coils, a lot of times I see that people are getting too much information. You're never going to be able to match a coil schedule exactly unless you were the basis of design. You basically need to just select a coil that meets or exceeds the desired capacity or leaving air temperature without exceeding the maximum water flow by too much. And then just keep an eye on the water side pressure drops. So, how many coils should I select? Well, most people don't want 3 or 4 row coils. So, usually you're only selecting between a 1 row or 2 row coil. One thing that people need to look out for is low water flow. I see a lot of people scheduling water flows in fractions of a GPM, and that it just doesn't make sense. Our coil selection program does a calculation for the Reynolds number and will allow selections in the top 50% of transitional flow. But once you go below the top half of the transitional flow mode, that's when your MBH, your heat capacity calculations become unreliable and are usually overstated. So we want to stay away from that. And we also don't want to select at the minimum recommended GPM, or we're going to have very poor valve authority, poor control valve operation. The valve is going to be just cracked open, then closed, and then just cracked open. It's just not, it's going to act, your modulating water valve would just act like a 2-position valve. Another thing we have to contend with is low water temperatures. Back in the good old days, everybody had 180-degree water. Nowadays, I'm seeing a lot of 110 and 120-degree water. The heat requirement may be the same, but something's got to change. We can offer, more rows, but that's more air pressure drop that you got to push the air through all the time. We can give you 12 fin per inch coils instead of 10 fin per inch coils, but that doesn't really give you very much difference in operation. The best solution to dealing with low water temperatures for single duct boxes is what we now offer as an enlarged casing option. That gives you increased fin area, which gives you increased capacity, a standard fin count, and the lowest cost. It's basically by giving you more face area on the coil, that is the best solution for dealing with low water temperatures. Don't add bros. Now, here's an ideal terminal unit installation. We want to size our inlet duct, our approaching inlet duct for less than 2,000 feet per minute. It'd be nice to have 3 diameters of straight approach. Put the boxes high above the ceiling if at all possible. Have a ceiling if at all possible. As far as hangers, I get a lot of questions on hangers. There's nothing wrong with using, a spring hanger, spring isolated hangers. The boxes are actually tested and rated, hung rigidly, but the spring isolators can give you insurance against unforeseen issues at the job site. Then we usually want to size our discharge duct for no more than 1,000 feet per minute. We want to have at least 4 feet of lined duct before our first diffuser takeoff, just because that can soak up a lot of fan noise. Then we want to have a high quality lined flex duct going to our diffusers because that can remove a lot of discharge sound. Hopefully I covered everything that I meant to cover. You want to use the correct exhaust terminal. Series fan box with ECM is really the state of the art right now for fan terminals. Size your VAV inlets for 2,000 feet per minute. Select PSC fans in the top 25% of the range. Select ECM fans in the bottom 50%. Limit your leaving air temperatures. And select coils to meet the leaving air or MBH requirements without exceeding the maximum GPMs by too much. And then remember that enlarged casings can help mitigate low water temperatures. And as always, proper installation can help ensure proper performance. Well, it's been my pleasure talking to you today. So I guess now I'll turn it back over to Tracy.